Okay. Yeah, so as I was saying, we're going to be going over some topics in number theory, specifically the greatest common denominator, but also the least common multiple, prime factorization, and a lot of other stuff to do with the divisors and multiples of something. Okay. So in order to define the least common multiple and greatest common denominator, we need to do some definitions. Okay. And usually on the AMCs, there's at least a few that are explicitly greatest common denominator or least common multiple on the AMC 10. On the AMC 8, you might still usually have some in the later, like from number 20 to number 25. That's a greatest common denominator style topic problem, but it's definitely not very common on the AMC 8. This is mostly an AMC 10 topic, like most number theory problems. And usually all of them are solved by the same technique, prime factorization analysis. The very fancy name for this is p-adic valuation. Okay, so, and here's some notation for divisibility. So you probably already know what a divisor is, but here's the formal definition. A divides B if there's some integer such that AC equals B, which means, notice that C can be negative or 0 or positive. So we can say -2 is a divisor of 4 and 2 is a divisor of -4. Right. So usually they'll specify it's a positive divisor or non-negative divisor or something like that to get rid of the negative ones, because they're kind of not useful in problems because it's not typically what you think of a divisor, but these are still technically a divisor of the number here. And an important definition to have, important notation to have down is this thing here. You might not know what this is here before, but this is a pretty common way to say A is a divisor of B. So just like substitute A is a divisor of B here. Every time you see this symbol. Okay, here's some basic ways to manipulate stuff using this notation. So if the first one is if A is a divisor of B and B is a divisor of C, then A is a divisor of C. The proof is pretty simple. Say B equals AC1 and C, actually this should be D1, C equals B D2. Then we have C equals A D1 D2. D1 D2 is an integer, so A's a divisor of C. And sometimes you'll see people like just go like this. A is the divisor of B, and B is the divisor of C, which is a common way to like show this relationship here. I'm not sure if this is like actually formally correct, but it's kind of common. Okay, and if A is the divisor of B, then A is the divisor of BC for all integers C. So basically, if A is the divisor of B, then A is also a divisor of all multiples of B. And again, this is integer, not just positive integer. If A is the divisor of B and A is the divisor of C, then A is the divisor of B plus C, and A is the divisor of B minus C. Okay, this one's a bit more non-intuitive, maybe, depending on how much you've like used this before. So the proof is, if B equals A D1 and C equals A D2, then B plus C equals A times parentheses D1 plus D2, and B minus C is this, A times D1 minus D2. These are integers still. And remember, we say something's A is a divisor of B if there's some integer C such that AC equals B. Okay. And now we can go on to defining the greatest common denominator and least common multiple. So we can say the greatest common divisor of like this set of integers. This is a bunch of integers. It's the largest positive integer such that it divides all of these. Okay, so I'll write this out in words in case you don't understand the notation here. So I'll just call this K for simplicity. So K is the divisor of A1, A2, and it is the largest possible. Great. So also keep in mind this is now a positive integer. And I don't think this positive integer differentiate it's not actually going to change anything here, because the greatest common denominator like chooses the greatest divisor, so it's going to be positive anyways. But it does make a difference here, which is why it's bolded. Because remember what I was saying about like technically this could be like -8, and negative like 2 is the divisor of -8. Well, basically we could just like choose some super big negative number here. Like we could make it as large as we want, and it'll not be defined. Okay, and here's the actual definition. So least common multiple of this set of integers is the smallest positive integer such that all of these numbers are a divisor of this least common multiple. Okay, so it's like a really similar definition to the greatest common denominator, except it's flipped. Okay, here's our first really useful fact that's going to actually appear on math competitions. So, for positive integers a, b, we have this relationship between the greatest common denominator and the least common multiple. So, how do we prove it? Okay, so I'm going to use something we'll go over more in depth later, which is the fundamental theorem of arithmetic. So we can prime factorize. It says there's a unique prime factorization for each integer, for each positive integer. Okay, hopefully you guys already know about prime factorization, because we're going to basically skip over how you actually prime factorize here. Okay. So let's write say a equals this. Wait, hold on. Oh shoot. Okay. K1, I guess here. Wait, no. Hold on, I'm running out of letters to use. Okay, I guess I'll use E. And note that this prime factorization here goes on to infinity. So basically we're listing all of the primes out here, and we're looking at the number of that primes in both A and B. Okay, so it's not like a normal prime factorization here. And also, exponents can be 0. Okay, and so the number of prime pi here is the minimum of qi and ei, which is the exponents in A and B. Hopefully you see why. It's because, so in order for something to be the greatest common denominator, we want it to be as large as possible, right? But it also has to be a divisor of both A and B. So it can't have a larger exponent of pi than A and B, right? So it has to be minimum of so the exponent of pi in the greatest common denominator is the minimum. And for a very similar reason, this is the max of qi ei. And when we multiply these two numbers, we add their exponents. Great. So now we want to prove. So now this is equivalent to the following statement. Okay. So this is. So we could use actually it's kind of, this is going to seem like magic here, but without loss of generality, qi is less than ei. Because if it's the other way around, we just switch A and B. And then we have, this is just true. This is very obviously true. Okay, and then we'll be going over some exercises now, which are basically just edge cases. Okay, so what are the divisors of 0? You can put your answer in the chat. Okay, so Caitlin says all numbers except for 0. Well, 0 actually still is a divisor because 0 times 0 is still 0. And remember, C can be 0 here. Okay, and so for any integer, k times 0 equals 0. Oh, well, I should say a to be more consistent. So a times 0 equals 0. So this seems kind of dumb. It's not. It's kind of unintuitive to think of like 1 as a divisor of 0, because 1 is bigger than 0. How can it divide? But this is what you get from the definition of a divisor here. Okay, here is the reverse. So what number does 0 divide? So remember, A is a divisor of B if there's some integer C such that AC equals B. So AC, so A and AC row here. Okay, and again, you can put your answer in the chat. Okay, so moving on. So once we plug in 0 into this equation here, we get 0 times c equals b. And this is going to just be 0 on the left hand side. So b equals 0. 0 is the 0 is the only multiple of 0. Now we want to find the greatest denominator of 0 and 8. And remember, this is positive integers for the greatest common denominator. So the greatest common denominator is a common divisor of both 0 and 8. Now we have established before that all numbers are a divisor of 0. So what's the divisor of 8 now? It's going to be, wait. So we have, these are all of the positive divisors of 8. All of them are also positive divisors of 0. And we just choose the smallest, we choose like the biggest one here. So, okay, and here's a more open-ended question. Why isn't the least common multiple of 0 and 8 defined? Like, why is it that we can't give any value to this, notation here? Again, so what are the multiples of 0? And remember, LCM is positive. Okay, so only 0 is a multiple, and because 0 is not positive, there is no LCM of 0 and 8. Like, there's no such positive integer that's both a multiple of 0 and 8. And in general, LCM 0k is undefined for k that's not 0. Or, well, for k, for all k. Because you can't get a multiple of 0 that's positive. Okay, now we're going to be going over some more useful like knowledge. And I've mentioned this before, but this says there's a unique prime factorization. So I'm going to be assuming all of you know what a prime factorization is. If you don't, just let me know and I'll explain more. Okay, so here's a very, very common formula in competition. So, this is kind of too much highlighting. So, if the prime factorization is this, okay, which kind of looks scary, but it's not actually, because it's just a lot of variables and indexes. So, and then we get the following like expression for the number of positive divisors. Okay, so where does this come from? So basically, we know the following fact about a divisor. So if the divisor has say EI factors of PI, then EI has to be less than or equal to QI. Okay, and EI can range from 0 to QI. And each of these EIs are independent. So for each of them, we can choose the so for each prime PI, we can choose the exponent in the divisor independently. For there's like QI plus 1 choices for each. Or wait, shoot. Oh shoot, this should say Q here instead of P. Yeah, anyways, so we can multiply all of these choices together because independent. Okay, so does that make sense here? Okay, I'm just going to give a few seconds to digest the proof. Okay. So now we have the sum of divisors, which is actually very similar to the previous proof in terms of the ideas here. So again, we write out the prime factorization. And we get this big formula here, which is really bizarre seeming, because like, how do you even get this? Well, this kind of gives a hint. Because, so like, these are all of the exponents of pi that divide, or well, not exponents, powers of pi that divide n. Okay, so, and our first step to like derive this formula is, well, now we're starting basically with the formula and showing that this works. Okay, so this is a well-known algebraic identity. Maybe you know it better if I write it out as this. Okay, and this gives you every possible power of like pi that could be like it in the divisor of n. Okay, and we're actually going to use something you probably already know, but like a much more amped up version. So this is basically the distributive property supercharged. When we're multiplying all of this stuff out here, we're going to actually combine each of these powers, like combine every possible combination, like we choose one from each group here. We're going to get one of each of those combinations, and each of those combinations is a divisor. So we get every single possible divisor in our sum. And that's how, like, this is how the formula works here. We're using the independence of each prime again. Okay, does that make sense? Okay, so does anyone have any questions about the proof here? Because if not, we're going to just like move on. But this is a very important formula in competition math, because that's just like really useful and it comes up often. Okay, and we'll be going over some exercises then, if there's no questions. So finding prime factorization of 216. You guys can answer in the chat again. Okay, yeah, Chris is correct. It's just this here. And this is unique by fundamental theorem of arithmetic. Oh, okay, and whoops, the solutions are right on here, but finding them with divisor of 216. And using our prime factorization from before. So we recall our formula here. We look at the exponents, and then we plus 1 to each of them, and then we add all of them up to get the number of divisors. So this is a very direct application of the formula here. I kind of like went over it again, the kind of like the proof, but yeah, you can just apply the formula directly. Okay, and this one isn't spoiled. Find the sum of the divisor of 216. Using the formula that we like went over before, because well, unless you're going to like add up all 16 divisors. Okay, and remember the prime factorization is this here. Okay, yeah. So directly applying formula here, we have this. Okay. And we just like do some like calculations here. So it is 80 times. Yep, so this is indeed 600, like Alan said. Okay, and here we're going to talk about this fact, which is like maybe not too obvious to you right now, but yeah. Okay, so again, looking at our prime, so again, let this be prime factorization of the number here. Then the number of divisors is this, right? So if this is odd, all of these are odd. Because like if there's a single even number, it's going to be even, right? When you multiply all of them together. So since all of these are odd, Q1, K2, QK are all even. And because they're all even, it's going to be a square root, right? Because like the exponents are even, you just can't like just take the square root and half each of the exponents, and it's still going to be like an integer. You can also prove it by like pairing up each divisor d with n over d, and this will, and you could do this for like all of the divisors except for square root n, because like square root n gets paired with itself, which is like not how it works. They have to be different. And this is actually I think it's actually a much more intuitive proof. So I'm going to give like a kind of like trick example. So like look at 6. So 1 gets paired with 6, 2 gets paired with 3. If we look at 16, 1 gets paired with 16, 2 gets paired with 8. 4 doesn't get paired up at all. And so this is odd, but this is even. Okay. And this is like a problem that uses this fact very directly. Okay, so it's kind of long, but hopefully you guys understand what it's saying here. Okay, now give you guys a few minutes to read, and then I'll go for the solution. Okay, so Caitlin actually has the correct answer here. It is indeed 4. Okay, so let's go. Okay, shoot. There's no. Okay, so I'm going to actually have to make a new page here real quickly because there's not enough pages here to go over the solution. Okay. Okay, I guess hopefully all of you guys like understand the problem now. If not, I'll just go back to the other slide. Okay, so the first step we can look at each locker individually. Like instead of looking at students, we look at lockers. And how, so locker I is like toggled by all divisors of I. Right, so like locker 6 is toggled by, okay, now I'm using the word toggled here to like refer to like them flipping open and like closed the lockers because and locker 6 is toggled by students 1, 2, 3, 6. Okay, and then that means it will be closed at the end because it's like toggled an even number of times. Okay, and then this brings us to our second step. Okay, and I should organize it a bit better because so this is the first step, this is the second step. So now a locker is open at the end if it is toggled a odd amount of times, which is the same as odd number of divisors, which is the same as being a square number. And from 1 to 20, there are 4 squares. Okay, nice. Oh, whoops, this is kind of messed up. It should be here. Okay, and don't be too intimidated. It's easier than it actually looks. It's not actually I think it'll probably be like a number in Amy number 6/7 nowadays. But yeah, it is a bit harder than the other examples we've gone over, so I'll give you some more time, about 5 minutes to like get a handle on it, and we'll go over the solution together. Let me check it's still recording. Okay, nice, it is recording. Okay, now I'll give you guys a few hints to kind of guide you on your solution. So Sn plus 1 equals Sn plus tau n plus 1. I believe that's the tau symbol. So if tau n plus 1 is even, Sn plus 1 and Sn have the same parity. If odd, switch parity. Okay. I guess actually I'm going to give you a few more minutes. Also, yeah, Alan and Chris are correct. It is 25. So, okay, now we're going. Okay, I'll go for the solution now that people have like gotten the answer. So this is kind of the same as my hint here. So tau n is odd if and only if n is a perfect square. We talked about this before. And so Sn is odd if n squared in an odd number of squares, because again from the hint Sn is, you can think of it being toggled whenever we go from Sn minus 1 to Sn, and we, which is going to be like Sn minus 1 plus tau n. If tau n is odd, which is equivalent to n being a perfect square. Okay, this is like kind of similar to the previous problem. We're just being, it's like being toggled on and off. Right, so like in if Sn if it's toggle, if it's if Sn is odd, it is toggled an odd number of times. Because S1 is, wait, hold on, so S1, yeah, S1 is 1, yeah, so okay, this should say greater than or equal to. Okay. Oh, okay. Yeah, and whoops. Turns out yeah, it should say it's toggled an even number of times. So like when you're jumping from here and here, so 1 to 2, nothing, it's not toggled. 2, 3, it's not toggled. 3 to 4, it is, because 4 is a square, so it's toggled 1 time here. And now the Sn is even, because it starts out odd here, and then when it's toggled it switches parity. And here is a very explicit characterization here. It's so once we've like figured out like the previous step, we can now like do some algebra, and like now we can calculate actually A and B here, because remember what we're trying to ask, we're trying to find here. We're trying to find A and B, where A is the number of positive integers with Sn odd and B is the number of positive integers with Sn even. So A equals, so the first interval here is 1 squared to 2 squared minus 1 inclusive, which is 2 squared minus 1 squared. And similarly, the other intervals are like this. And notice 2020, wait, no, it's not 2020, it's 2000. Whoops. It's 2005, yes, it is 2005. 2005 is between 45 squared and 44 squared. So we're going to get, I believe, okay, so it's like this here for A, and B is 3 squared minus 2 squared plus 2005 minus 44 squared plus 1 . Yeah, so anyways, so and where can I write? So using the difference of squares formula, we can get A equals 3 plus 7 plus 87. B equals 1 plus 5 plus 9 dot dot. And the last normal term here is like 43 squared minus 42 squared, which is 85, plus what is this? 2005 minus hopefully I'm not messing this up. 69 plus 1. Okay, so a minus b is -2, -2, -2. Because we can just pair these up here. Either it's going to be like what? There's going to be 87 minus 3 divided by 4 plus 1 of these terms here, which is going to leave us with 22 of these plus, hold up, let me see where I'm messing up here. It's probably okay, I'm actually not. Wait, oh, it might be because I'm. Wait, 26. Okay, I'm actually not entirely sure how I'm messing up here. I'm guessing I'm somehow messing up on this equality case here. It should be 69 here, actually. Instead of... Okay. And that's how we get 25. Okay, there's another exercise here. I'm actually going to skip this and come back at the end if we have some time. So we're going to go over prime factorization now. We've talked about prime factorization before a lot, obviously. But we're going to actually talk about how to do like actual analysis on prime factorization. Okay, here's an exercise. Whoops. Okay, well, okay, we're going to actually go for this solution now. Okay, so we're using the one of the facts we went over in the beginning. So the greatest common denominator times the least common multiple is equal to product of the two numbers. And so we can just multiply these two like given values together to get, we have AB equals 20 factorial. Okay, and here is a very, very common trick. So if you have GCD of A and B equals like K, do the substitution A prime equals A divided by K, B prime equals B over K. So the greatest common denominator of like A prime and B prime is now 1. Okay, nice. So now the least common multiple in terms of like the new variables is like 20xy. Because again, remember wait. xy equals AB divided by 20. So 20 factorial divided by 20 equals 19 factorial by 20. And then because like the greatest common denominator is 1, we have the least common multiple is yes, because they still multiply to like xy. Okay, and now notice that like x and y correspond to A and B, obviously, because like x equals like A divided by 20 twice B divided by 20. Okay, so now we're going to like actually do some prime factorization analysis here. So say there's like a pi like qi and 90 factorial divided by 20. So in order for xy equals like this, we have to assign like these primes somewhere in x and y, but again, so they have a greatest common denominator of 1. So they can't share any prime. So all of these primes must go to one of x and y. And then basically we just check how many factors divide by how many primes divide 19 factorial divided by 20. And like say this number is like x, and it's gonna be 2x because we can choose. Or wait, actually, I should choose a better number because variable because x is already taken. Say it's like L, then it's going to be like 2L. Because for each prime, we choose if it all goes to x or y. Oh, excuse me. Right, so how many primes divide 19 factorial divided by 20? So we can use some common sense stuff here. So 19 factorial has 2, 3, 5, 7, 11, 13, 17, 19. All of these are still going to be there when we divide by 20. And when we divide by 20, we get rid of 2 factors of 2 and 1 factor of 5. But 19 factorial already has 3 factors of 5, right? Or, yeah, so it's 3 factors of 5 and a bunch of factors of 2. So when, oh shoot, okay. So when we divide, there's still going to be 2 and 5s. Okay, shoot, I'm accidentally pressing buttons. That's messing me up. We still have okay, and there's still all of these primes are going to still be there. We have 8 primes. L equals 8, and we get 2 to the 8, which is 256. Okay, nice. And now we have an old Amy problem. Again, it's like kind of a high placing, but it's easier than it looks here, actually. I'll give you like 5 minutes to look at it. Okay, let's go. We're kind of running out of time, so I'm going to actually like speed this up here. Okay, so now we prime factorize A and B, and notice because only so like we're given at least common multiples of a bunch of like pairs of these, right? So all of these only have 2 and 5. So A, B, C can only have 2 and 5. Because otherwise, like, any prime, like, if it was in A, B, C, would have to, like, show up in the least common multiple, because it's, like, a multiple. And then, I've already talked about this before, the maximums, like, the least common multiple, like, for the least common multiple, you take the maximum of each exponent. Okay, so, and this is how we get, like, this, like, system of equations here. So, max BC equals 4, and max CA equals 4, and max AB equals 3, implies the following facts here. So, A, B are less than 3, right? So none of these, none of A, B can be 4. So C must be 4. Right. So now we have one of wait, what? So one of AB is 3, and the other one is like 0, 1, 2, 3. And we need to subtract overlap when both are 3. And the result of this is like 4 plus 4 minus 1 equals 7, weighs 4 ABC. And notice we're talking about like the prime factors of 2 here. And now we're going to look at the prime factors of 5. Okay, so we have all of them are 3. So, So they're all are 3, or 2 are 3. Well, okay, so at least 2 of them must be 3. If only 1 is 3, then the other 2 max will be less than 3. And that's a contradiction. If at least 2, then like in each pair we'll have at least 1 3. Okay. And okay, so now we just like find a phrase to get this. This is 1, this is 3 times, I believe, because this could be 0, 1, 2. And which one of these is x? Determine x. So 9 plus 1 equals 10. Ways for x, y, z. And x, y, z and a, b, c are independent. Okay, and that's like kind of a word I'm using a lot, independent, because fundamentally, prime factorization analysis relies on the fact that like each of these primes are independent. Right, so we multiply 7 times 10 to get our final answer of 70. Okay, and here's our last problem here. I'll give you like 2 minutes and then we'll go over it. This will probably be our last problem for a day. Yeah. Okay, and Okay. Oh yeah, 405. I believe. Yeah, it is correct answer. Okay, so let's go over the solution. So n has 60 positive factors, and this is a synonym for divisors. So, and we want to compute the largest number of positive divisors that n squared could have. Okay, so our first step is again creating the prime factorization. Right, that's our first step in all of these problems. Create a prime factorization because this is the prime factorization section. And we have this here. And the prime factorization of 60 is this here. Okay, well actually that's not like strictly needed, but it's like useful for like, yeah. Okay, and n squared divisor, n squared has this many divisors. To maximize, oh shoot, we want to make all of the divisors as close as possible. And this occurs at here. Oh wait. Yeah, again this should be Q here. Whoops. Okay, so and the best way to maximize is to make all of them roughly equal. And yeah, so in general, when you want to maximize a product, you want to make all of the terms as equal as possible. In general, that's like how you maximize. So, and this happens when, and the best way to make them equal is to use as many terms as possible. And again, the prime factorization is this, and so this is going to be 1 plus 1, 1 plus 1, 2 plus 1, 4 plus 1, which is how we get Q1 equals 1, Q2 equals 1, Q3 equals 2, Q4 equals 4, and then we just like plug this back in to get 3 times 3 times 5 times 9, which is 405. Okay, so we have actually finished, which is very nice, except for like one problem here. Okay, I'll give you a very quick solution here. Finding number of positive cubes that divide 3 factorial times 5 factorial times 7 factorial. So 3 factorial is 2 times 3, 5 factorials. 2 squared times 3 times 5. Or right here. Okay, and this is just like, you can just multiply it out, and they're pretty small factorials, so it's like not too hard to do, just like manually. On the other hand, you could like use or like draw legend trace theorem or something like that to help you out. Okay, so adding all of these up here. Okay, and a cube, say the cube's like prime factorization is like this here. It's like 2a times 3b times 5c times 7 to the power of d. So since it's a cube, all of the exponents are going to be multiples of 3. And for a, so a can be 0, 3, 6, b equals 0, 3, c equals 0, d equals 0. And so, like, all of these are independent, again. So, we get 6 for multiplying all of the possible choices. Okay, so now we've finally finished every single problem in this very long slideshow. Okay, so does anyone have any like questions? Okay, so if there's no questions, then this is the end of today's lesson. And yeah, I think this is probably the end of Magic Math for the year, unless we do some summer lessons, which is to be determined. Or, yeah, so thank you guys for coming and listening to me talk. Okay, and have a good weekend. Okay, and you're welcome.